Hi everyone, welcome to our Deconstructing Robotics session. Today, we will dive into what happens behind a robot's brain by taking a behind the scenes look at WALL-E here and also one of our own robots. I'm Cherie, a robotics PhD student at Carnegie Mellon, and I work on helping robots be safer in challenging environments. For example, here is my robot zipping through a mine.
And my name is Pragna and Paloma, also a PhD robotics student at Carnegie Mellon University. I work on making robot hands and using them to do everyday tasks like picking a grape off a stem shown here.
And I am Paloma, a PhD student in robotics at Carnegie Mellon University. I help robots perceive the world using different senses ranging from touch to vision to sound. Let's start today by looking at what a typical day in WALL-E's life looks like. WALL-E starts by getting out of bed, driving around to find some trash, which it then scoops up and compresses into tiny little cubes, which it then stacks together, and then repeats this process over and over again. So at a high level, WALL-E's goal is to find trash and pick it up. But how should WALL-E go about solving this goal? Well, first, it has to sense the world to find the trash. Then it has to plan, that is, think ahead of general motions that make it reach the trash. Finally, it has to act so as to execute the planned motions. This cycle is commonly referred to as the sense, plan, act cycle in robotics. Let's begin with how WALL-E senses the world to find the trash. Let's see how the world looks like through WALL-E's eyes. Now, looking at this image, WALL-E has to answer the question, which one of these is trash? Now, WALL-E would break down this problem by dividing up the scene into a bunch of grid cells. It can then scan each cell one by one and ask a second question. Is there trash in this cell? So let's analyze this by picking a cell and zooming in to see how it looks like. So do you see any trash in this cell? Well, no, this cell contains just sand. Okay, let's pick another cell and repeat this by zooming into it and asking ourselves, how about now? Do you see any trash in this cell? Well, yes, that does look like a trash microwave. Okay, so now we want WALL-E to do the same exercise. How does WALL-E learn to tell what is trash and what is not trash? Well, one way for WALL-E is to use all of the images it has seen in its past experience to classify something as trash or not trash. So in the first column here, we have a set of images of trash that WALL-E has seen in the past. And here in the second column is another set of images of things that it has seen that are not trash. So let's do an exercise. On the left is the image of what WALL-E is currently seeing from the grid cells that we saw earlier. Now, can you guess which past image is this image most similar to? As you might have guessed, it is the image of this trashed microwave. Now, once WALL-E has matched the current image it is seeing to an image from its past, it can then ask, is this image of trash or not trash? And yes, indeed, it is in the first column, which is trash. Okay, let's repeat the same exercise on a different image from the grid. Now on the left again is the image of what WALL-E is currently seeing. Can you again guess which past image is this most similar to? As you might have guessed, this is the image on the top right. Now, is this image of trash or not trash? And no, this is not trash. It is just sand like we saw earlier. So This effectively is how Wall-E is able to do classification of trash versus not trash based on images of similar looking things it has seen in the past. Okay, so now that Wall-E has correctly identified trash in the image, it has to move towards it. But in order to move towards the trash, it has to then go from 2D location of trash on the image to actual 3D location in the real world. How does Wall-E locate trash like this in the real world? Well, Wall-E, just like us, has two eyes, and each eye captures an image of the same trash can, but with a slight offset. This offset lets Wall-E triangulate the position of the trash can seen here from 2D images into a 3D world location, X, Y, Z, that you can see on the left. Okay, great. Now that we have all the sense components, let's do a fun exercise. In this exercise, we will start by holding out our finger at a close distance from our eyes. Now that we have a finger here, let's close our left eye and observe where the finger is. Then let's close our right eye and again observe where the finger is. Now repeat this process of closing the left eye, then the right eye, and then the left eye. And observe how much the finger moves as you do this. Okay, great. Now let's repeat the same process, but the finger much further out. So let's start by closing our left eye, then closing our right eye, and we'll do the same thing and observe how much the finger moves as we close our left eye, then our right eye. Okay, so you bring your finger close and close your left eye and right eye, and then you move your finger further back and then close your left eye and right eye. Every time you do this, you will observe that your finger moves laterally. Now, the question is the lateral movement of the finger greater when the finger is closer or when the finger is further out? What do you think? Well, as you will see that the finger does move a lot more when the finger is close by and moves a lot less when the finger is further out. So how much the finger is moving between the left eye and the right eye tells us about how far the finger is from our eyes. And this is exactly how we, as well as Wall-E, with our two eyes, are able to locate an object in the 3D world from just 2D image locations.
Awesome. Now that we know where the trash is with respect to Wall-E, we can now think ahead and plan general motions Wall-E should take in order to go to the trash and pick it up. Let's go back to a day in Wall-E's life. Wall-E zips around, avoids obstacles, finds the trash, and finally scoops it. So the problem of finding these general motions is called the planning problem. We will focus on the first step, where Wall-E should get to the trash quickly without crashing into our very valuable plant here. This problem becomes difficult because there are so many options that Wall-E should choose from, and there are so many decisions that needs to be made. So instead, we often simplify the problem with motion primitives, which describes a few samples of general motions that the robot can take. For example, here we have 3 motion primitives that Wall-E can take. Wall-E is a bit like a car, so it can go left in this arc shape, go in a straight line, or take a right turn. Let's see how we can use these primitives for the planning problem. Here we have Wall-E as a blue triangle, waiting to get to the microwave at the top right corner, while avoiding the plants. So to plan, at each stage, we follow 3 steps. First, we remove actions that collide with obstacles. So let's step through this together. We can see here we removed the right turn because it collided with the plant. Now between the left and the straight action, we pick the primitive that gets us closest to the goal, which is straight ahead. So with this primitive locked in, we advance forward. And then we repeat this process until we reach the goal. So let's do it again. Let's first remove unsafe actions, which is the left turn here. Removed. Then we pick the safe primitive that gets us closest to the goal, the right turn. So here, let's combine the two steps. There's no actions that are in collision. And then we pick the safe primitive that's closest to the goal. We go left. And here we go straight. There we go. Wally is at his destination. Now please pause here and try the planning problem yourself. Use our 3 motion primitives to get Wall-E to the microwave without crashing. So here we have Wall-E going straight, then it turns left, sneaks between the obstacles, and then finally turn right, then straight to the microwave. So now we know how to blend general paths with motion primitives for Wall-E to get to the trash without colliding. We also have our second stage. Now that Wall-E can get to the trash, we also need to scoop the trash into its tummy. So we can also think of this scooping action as a combination of motion primitives. With these arc movements with his arm, the bending of his hands as different motion primitives that he can choose from. For example, here, what Wall-E is doing can be described in 3 primitives. He pushes his arm out right here, folds his hands in, and then pulls the trash. All right, now to act. We know the general motions Wall-E should take in order to achieve his overall goal. We now need to move his motors, wheels, and hands to execute on the plan. Let's focus on getting Wall-E to the trash. We had a planned path in gray from the last stage, and Wall-E needs to figure out how to steer and move his wheels and motors in order to follow this planned path. Because what happens if we don't steer correctly? Wall-E may fall off his path and hit an obstacle that we didn't account for. And this difference between the planned path in gray and the blue path in blue results in an error. So this question becomes, how can we deal with errors so we don't crash? Here, the key idea is feedback, where we ask for feedback, which is measuring the error. Then we steer in the direction or move to make the error smaller. And then we repeat this process every step of the way. Let's step through an example of a car that wants to follow this planned path. First, the car is off the path. So first, we measure the error, which shows that the car is to the right of the planned path. Then we steer left in order to make the error smaller. Oh no, we corrected too much. Don't worry, we measure the error again, which tells us that we're to the left of the line. Then we steer right to correct for it. This idea of using feedback to correct for the errors is called a feedback controller. Try it yourself with a car following a straight path. Draw out the error arrows and also the steering directions that you think are needed to correct. Let's step through. For the first car, we first measure the error, which is that the car is to the left of the line. So we steer right. In the second car, we steer left. And in the third car, we steer right again. Great. So now we know how to act and correct for errors with a feedback controller to get Wall-E to his goal. Nice. So Wally has now successfully found the trash, got there, picked it up by using the sense, plan, and act cycle. Wally first locates the trash with his eyes in 3D. Then we plan general motions Wally should take in order to achieve its goal. Then finally, we act on the plan and adjust for the errors on the way to complete the goal.
Now let's learn about Delta robot manipulators. Unlike Wall-E, these robots are stationary, but they can still interact with objects around them. This specific robot here is called Delta Z, made by my colleagues at Carnegie Mellon University and Rose-Hulman Institute of Technology. It is made from 3D printed material and can move in X, Y, and Z, as you can see in the video here. You can actually make your own Delta robot using the link in the bottom right corner. Here we have a simple task of the Delta robot kicking a ball into the goal. So what does this robot need to accomplish this task? Think back to the sense, plan, act steps that we did for Wall-E. First, let's think about what we used to accomplish the task that we did with localizing the trash and picking it up with Wall-E. We had computer vision, a feedback controller, and motion primitives. Connect these to the plan, act, and sense steps on the left. Here we'll take a look at the answers. Plan connects to motion primitive, act connects to feedback controller, and sense connects to computer vision. I'll go over each of these individually. What do we need for a robot to be able to sense? We need computer vision and localization. This is similar to how Wall-E used his eyes or stereo vision to be able to localize the trash and the difference between what is trash and what isn't trash to accomplish his task. For us, we need vision sensing for the XYZ location of the ball and the XYZ location of the goal. So you can imagine a stereo camera, as we talked about previously, with the shifting of the finger position when you cover each one of your eyes. Here we have a camera out of frame that is able to detect the XYZ position of the ball and the goal separately so that we can plan how to get the ball into the goal. What do we need to plan our task? For our foot to be able to kick the ball, we need to think about the paths that the foot can take. This is like Wall-E planning which path to take to be able to get to the trash. So here we'll use motion primitives. Similar to Wall-E, we have several paths that our foot here can take. We can only take straight paths, and I'll show you a few possible paths. The first one goes to the left of the ball and back. Then we go to the right of the ball and back. So those two didn't work. Let's try going straight forward, and then we've made our goal. Now what do we need to act? For acting, we need a feedback controller. This is similar to our example of the car and being able to steer it into a desired position and account for the error between where we currently are and where we want to be. Similarly, we want our motors and the foot to be in a desired position in X, Y, and Z. Let's suppose that the foot stopped just before the ball. Here we can say that the error is this red arrow, and we can move the foot to the end of this arrow to adjust for the error. Now let's take a look at Delta robots in the wild. Here we have a Delta robot that can draw and write. We've attached a colored pencil instead of the foot to the same white soft material Delta. You can see that because of the soft material, the pencil is able to draw these curves and lines as we do when we write. Next, we have a simple hook design attached to our delta to pick up a small 3D printed weight and move it to a new desired location. This is called a pick and place task. Finally, we have a stamping task. So we have an ink pad to the left, and then the delta moves a stamp into the ink pad and then onto a piece of paper to print the letter C. Our last segment for the session is called Spot the Error, where we'll show videos of robots failing and we talk about why they went wrong. Here we have a Roomba falling down the stairs. Let's talk about what in the sense, plan, act steps went wrong. What do you think went wrong? So here we think that the sense step could be improved because the Roomba didn't have a way to know that there were stairs there. And it should have been able to know that there is no plan that can get it successfully down the stairs to accomplish its goal of continuing to clean the house. Our last and final example here is for a small humanoid robot who is dancing and falls over. Here we want the robot to be able to continue to walk, dance, and do the actions we want it to do. So what do we think failed in the sense, plan, act steps for this robot to be able to continue as it were? Here we say that the act failed because the feedback controller can sense the error between where the robot is and where it wants to be. And when the error is too large, the robot isn't able to adjust. It's basically picking up momentum that it's not able to counteract, which results in falling. Thank you for watching our session on deconstructing robotics.